Hello and welcome. Today we're going to take a peaceful journey through space, exploring the true size of the universe. There's no rush, no urgency, just a calm conversation about something truly extraordinary. You might be lying down, sitting comfortably, or simply relaxing as we explore together the immensity of the cosmos. You don't need to look at the screen. You don't need to take notes. Just listen and let your mind travel gently. Through the distances we're going to discover, the universe is incredibly large, but we'll understand this step by step, starting very small, very close to home, and then, slowly, we'll move away, further and further. With each moment, we'll add a new layer of understanding, smoothly, without surprises. Think of this video as a long walk through knowledge, where each step is comfortable, predictable, and relaxing. We'll start here, on Earth, our home, and then slowly, we'll expand our perspective until we reach the limits of what we can observe. Take a deep breath, and let's begin this journey together. The universe has a size, but understanding that size requires us to build up to it, gradually. We can't simply jump to the biggest numbers, because those numbers, without context, don't mean very much. Instead, we'll start with things we know, things we can picture, and from there, we'll expand, little by little. This is a journey of scale, a journey of perspective, and most importantly is a journey we'll take at a comfortable pace. So settle in, relax, and let's begin, right here, on our beautiful blue planet. Understanding the size of the universe is really about understanding scale. What does it mean for something to be large? Large compared to what? We understand the size of our room, our house, our neighborhood. These are scales we experience every day. But as we move beyond, to cities, into countries, into continents, our intuition starts to falter, and when we move beyond Earth, into space, our everyday experience becomes completely inadequate. We need new ways to think about distance, new comparisons, new perspectives. That's what we'll build together. Over the next few hours, we'll start with the familiar, and gradually, step by step, we'll venture into the unfamiliar, and along the way, we'll discover something remarkable, not just about the universe, but about ourselves, because we are part of this universe, made from the same matter, subject to the same laws, and somehow, despite being so small, so brief, we can understand it, we can measure it, calculate it, comprehend it. That's quite extraordinary when you think about it. A tiny species, on a tiny planet, orbiting a typical star in a typical galaxy, can look out into the cosmos and understand what it's looking at. We can measure distances, spanning billions of light years. We can calculate the age of the universe itself. We can understand how stars work, how galaxies form, how the universe came to be. This is one of humanity's greatest achievements, our ability to understand the universe we inhabit. So as we take this journey together, remember that. Remember that everything we're going to discuss, every distance, every scale, was measured and understood by humans. People like you and me, curious, persistent, patient, using nothing but careful observation, mathematics and reason. Now, let's begin our journey. Let's start where we are, right here, on Earth, our home, the only world we've ever known. Earth is, by our standards, quite large, but in the context of the universe, it's incredibly small, a pale blue dot, as the astronomer Carl Sagan once called it. But it's our pale blue dot, and it's where our story begins. So take another deep breath, relax, and let's explore the true size of the universe together. We'll move slowly, carefully, building our understanding, piece by piece. There's no rush, we have plenty of time, and by the end, you'll have a sense of just how vast, how incredible, how beautiful the universe really is. Are you ready? Then let's begin. Let's start with the ground beneath your feet, the planet we call home, Earth. Let's begin with Earth, our planet, our home, the place where everything we know, everyone we've ever known, has lived their entire lives. Earth is, by our everyday standards, quite large. If you were to walk around the entire planet, along the equator, You'd travel about 25,000 miles or roughly 40,000 kilometers. That's a very long walk. In fact, if you walked continuously, without stopping, at a normal walking pace of about 3 miles per hour, it would take you over 8,000 hours. That's about 333 days of continuous walking, nearly a year, without rest. So Earth is big, at least from our human perspective. The diameter of Earth, measuring straight through the middle, from one side to the other, is about 8,000 miles, or nearly 13,000 kilometers. Imagine that distance. From where you are right now, imagine traveling 8,000 miles in any direction. If you're in North America, you could travel to the other side of the planet, to the Indian Ocean. If you're in Europe, you could reach the middle of the Pacific Ocean. That's roughly the distance we're talking about. Earth is substantial. It has weight, mass, gravity that holds us gently to its surface. The mass of Earth is about 6 trillion kilograms. That's 6 followed by 24 zeros. It's hard to comprehend such a number, but it's enough mass to create a gravitational field that keeps our atmosphere in place, that keeps us on the ground, that keeps the moon in orbit around us. Everything we experience happens on this sphere. All of human history, every city, every ocean, every mountain exists on this one planet. When you think about it, Earth contains multitudes, nearly 8 billion people, millions of species of plants and animals, vast ecosystems, from the deepest ocean trenches to the highest mountain peaks. The Mariana Trench, the deepest point in Earth's oceans, is nearly 7 miles deep. If you could place Mount Everest, the highest mountain, at the bottom of the Mariana Trench, its peak would still be more than a mile underwater. The oceans themselves are vast. They cover about 71% of Earth's surface. The Pacific Ocean alone is larger than all of Earth's land area combined. And yet, when we start comparing Earth to other things in space, we'll see that it's actually quite small. Let's think about Earth's surface for a moment. The total surface area is about 197 million square miles, or about 510 million square kilometers. About 71% of that is covered by water, the oceans. The remaining 29% is land, 7 continents, and thousands of islands. On this land, humans have built civilizations, cities that stretch for miles, roads that connect one side of continents to the other. The longest road you could drive, and without crossing an ocean, would take you from Cape Town in South Africa all the way to Magadan in Russia, about 12,000 miles, at highway speeds, driving continuously. That would take you about a week. From space, at night, you can see the lights of our cities glowing against the darkness, forming patterns that trace out coastlines and river valleys. Those lights are a sign of our presence, our activity, our energy use. But even all of those lights and all of that human activity is just a thin film on the surface of this planet. If you could slice Earth in half, like cutting an apple, and look at the cross-section, you'd see layers. The crust of the thin outer shell where we live is only about 3 to 30 miles thick. Under the oceans, it's thinner, about 3 to 6 miles. Under the continents, it's thicker, up to 30 miles or more. But compared to Earth's total diameter of 8,000 miles, the crust is incredibly thin. It's like the skin on an apple. That's how thin the layer we live on really is. Below the crust is the mantle, a thick layer of hot rock that extends down about 1,800 miles. The mantle isn't liquid, exactly. It's solid rock, but it's so hot and under so much pressure that over very long periods of time, it can flow like thick honey. This flow in the mantle is what drives plate tectonics, the movement of continents, the formation of mountains, earthquakes, volcanoes. It all happens because of slow, steady circulation in the mantle. Below the mantle is the outer core. This is liquid, made primarily of iron and nickel. It extends from about 1,800 miles deep to about 3,200 miles deep. The outer core is incredibly hot, about 8,000 to 10,000 degrees Fahrenheit, as hot as the surface of the sun. This liquid iron circulating in the outer core generates Earth's magnetic field. That magnetic field is incredibly important. It protects us from harmful radiation from the sun. Without it, Earth's atmosphere would slowly be stripped away by the solar wind. At the very center is the inner core, solid iron and nickel, about 1,500 miles in diameter. The inner core is even hotter than the outer core, about 10,000 to 13,000 degrees Fahrenheit, but it's solid because the pressure is so immense that even at those temperatures, the iron cannot melt. The inner core spins slightly faster than the rest of the planet, about one extra rotation every 1,000 years or so. All of this, the entire structure of Earth, from the surface down to the center, came together about 4.5 billion years ago. Earth formed from a disk of dust and gas orbiting the young sun. Countless small particles collided and stuck together, gradually growing from dust to pebbles to rocks to mountains to a planet. In those early days, Earth was very different from today. There were no oceans, no atmosphere as we know it. The surface was molten rock, constantly bombarded by asteroids and comets. The impacts were so frequent, so violent, that the entire surface was kept molten. A global ocean of liquid rock. One of those impacts in about 4.5 billion years ago was particularly large. An object about the size of Mars crashed into the young Earth. The collision was catastrophic. It threw enormous amounts of material into orbit around Earth, and that material over time it came together, forming the Moon. After that impact, Earth slowly began to cool. The bombardment decreased, the surface solidified. Water vapor, trapped in the interior, was released through volcanic eruptions. It condensed in the atmosphere and fell as rain. For millions of years, it rained and rained and rained. Gradually, the oceans formed. An atmosphere developed, primarily from gases released by volcanoes. Carbon dioxide, water vapor, nitrogen. Over hundreds of millions of years, the atmosphere changed, evolved, and eventually, about 3.5 billion years ago, conditions became right for life to emerge. The first life was incredibly simple. Single-celled organisms, bacteria. But over time, over billions of years, life became more complex, more diverse. Plants evolved, animals evolved, complex ecosystems formed. About 540 million years ago, there was an explosion of diversity. Many of the major groups of animals that exist today appeared during this time. And about 200,000 years ago, modern humans appeared. We are very recent arrivals. If Earth's history were compressed into a single year, humans would appear in the last few minutes of December 31st. And yet, here we are, conscious, aware, able to contemplate our own existence and the planet we live on. Earth is our home. It's where we evolved. It's where we live. And despite being just a small rocky planet orbiting an ordinary star, it's the most important place in the universe to us. But now, let's step outside. Let's look beyond Earth. Let's visit our nearest neighbor in space, the Moon. The Moon orbits Earth at an average distance of about 240,000 miles, or roughly 385,000 kilometers. That might sound like a huge distance, and it is by our everyday experience. If you could drive a car to the Moon at highway speed, let's say 60 miles per hour, it would take you 4,000 hours. That's about 167 days of continuous driving, over 5 months and without stopping. The Moon itself is much smaller than Earth. Its diameter is only about 2,160 miles, or 3,500 kilometers. So you could fit roughly 4 moons, side by side, across the width of Earth. In terms of volume, about 50 moons would fit inside Earth. The Moon is, in cosmic terms, quite close to us. But even this short distance is difficult for us to truly comprehend. When we look up at the Moon at night, it seems close and almost within reach. We can see details on its surface, even with our naked eyes. But that distance, 240,000 miles, is already far beyond anything we experience in our daily lives. The Moon is the only other world that humans have ever walked on. Between 1969 and 1972, 12 astronauts, as part of the Apollo program, stepped onto its surface. Those journeys were extraordinary achievements. They required enormous rockets. The Saturn V, the most powerful rockets ever built. The journey to the moon took about 3 days. 3 days of traveling through the vacuum of space in a small capsule to reach our nearest neighbor. The astronauts saw Earth from the moon, a blue marble hanging in the blackness of space. They described it as fragile, beautiful, precious. Seeing Earth from that distance gave them a perspective that few humans have ever had. And what did those astronauts find? On the moon, a barren, airless world, grey dust and rocks, ancient lava plains, impact craters of all sizes, no air to breathe, no water to drink, no life of any kind. The surface is covered in a fine dust called regolith. It's made of tiny fragments of rock, ground down over billions of years by meteorite impacts. The regolith is everywhere. In some places, it's just a thin layer. In others, it's several meters deep. When the astronauts walked on it, their boots left perfect footprints, and those footprints are still there today, unchanged, because there's no wind on the moon, no rain, no weather of any kind. Without an atmosphere, the footprints will remain for millions of years, until eventually they're erased by new meteorite impacts. The moon has mountains, valleys, vast plains called maria, which is Latin for seas. Early astronomers, looking through telescopes, thought these dark areas were seas of water, but they're not. They're ancient lava flows billions of years ago. When the moon was young, volcanic eruptions filled large impact basins with molten rock. That rock cooled and solidified, forming the dark plains we see today. The moon also has enormous craters, the result of impacts from asteroids and comets over billions of years. Some of these craters are hundreds of miles across. One of the largest, the South Pole Aitken Basin, is about 1,600 miles in diameter and 8 miles deep. It's one of the largest impact craters in the entire solar system. The moon has no atmosphere, no magnetic field, no protection from space. Radiation from the sun, cosmic rays from deep space, and hit the surface directly. During the day, when the sun is overhead, the surface temperature can reach 260 degrees Fahrenheit or 127 degrees Celsius. At night, the temperature plummets to minus 280 degrees Fahrenheit or minus 173 degrees Celsius. These extreme temperature swings happen because there's no atmosphere to hold in the heat. The moon rotates very slowly. A day on the moon, from sunrise to sunrise, lasts about 29.5 Earth days, so the sun slowly moves across the sky, taking about 2 weeks to go from sunrise to sunset, then about 2 weeks of darkness. The moon is also tidally locked to Earth. That means it rotates at the same rate that it orbits Earth. As a result, the same side of the moon always faces Earth. We never see the far side from Earth, not because it's dark, but because it's always facing away from us. The far side was a mystery until 1959, when a Soviet spacecraft flew past and took the first photographs. It turns out the far side looks similar to the near side, but it has fewer of those dark maria, those ancient lava plains. The moon formed about 4.5 billion years ago, likely when a Mars-sized object collided with the early Earth. The impact was unimaginably violent. It threw enormous amounts of material from both Earth and the impactor into orbit around Earth. That material was incredibly hot, molten rock and vapor, orbiting in a ring around the young Earth. Over time, perhaps as little as a few decades, that material came together, cooling and solidifying, forming the moon. So the moon is made partly from Earth and partly from the object that hit us. It's a piece of our history, a remnant of that ancient collision. Since then, the moon has been our companion, orbiting Earth, creating tides in our oceans through its gravitational pull. The tides are caused by the moon's gravity, pulling on Earth's oceans. The side of Earth facing the moon is pulled slightly more than the center of Earth, and the side facing away is pulled slightly less. This creates two bulges in the oceans, one facing the moon, one facing away. As Earth rotates, these bulges move around the planet, creating high tides and low tides. The moon's gravity also affects Earth's rotation over millions of years, and it's been slowing us down. In the distant past, Earth rotated faster. A day was shorter. perhaps only 18 hours long, but the moon's gravitational pull has been gradually slowing our rotation, adding time to each day, and as Earth's rotation slows and the moon moves away from us, every year, the moon drifts about 1.5 inches farther from Earth. In the distant future, billions of years from now, the moon will be much farther away. Earth's days will be longer, the tides will be weaker, but that's far in the future. For now, the moon is our constant companion, the brightest object in our night sky. After the sun, it's been important to humans throughout history. We've used it to track time, to navigate, to inspire art and poetry, and it's the only other world we've ever set foot on. Someday, perhaps, we'll return, building bases on the moon, using its resources. Maybe even it will become a stepping stone to the rest of the solar system. But for now, it remains a silent, barren world, 240,000 miles away, always there, always watching. Our closest companion in the vastness of space. Now, let's continue our journey outward. Let's visit the center of our solar system, the source of light and warmth and life, the sun. The sun is dramatically larger than Earth. In fact, you could fit about 109 Earth side by side across the diameter of the sun. The sun's diameter is roughly 865,000 miles, or about 1.4 million kilometers. That's enormous. Compared to our planet, if the sun were hollow, you could fit about 1.3 million Earths inside it. 1.3 million. That's how much larger, in volume, the sun is compared to Earth. But size is only part of what makes the sun so impressive. The distance between Earth and the sun is where things really start to get interesting. Earth orbits the sun at an average distance of about 93 million miles, or roughly 150 million kilometers. We call this distance 1 astronomical unit, or simply 1 AU. Astronomers use this measurement as a convenient way to describe distances in our solar system. 93 million miles. Let's pause and think about that. If you could walk to the sun at a normal pace without stopping, it would take you to over 3,500 years and to arrive. If you drove at highway speed continuously, it would still take over 176 years. Even flying in a commercial airplane at 500 miles per hour would take you over 21 years to reach the sun. Light, which is the fastest thing in the universe, traveling at about 186,000 miles per second, takes about 8 minutes and 20 seconds and to travel from the sun to Earth. So when you look at the sun, you're seeing it as it was 8 minutes and 20 seconds ago. That's our first real glimpse of how distance in space also becomes distance in time. Nothing can travel faster than light. Not matter, not information, nothing. So whenever we look at anything in space, we're looking back in time. The farther away something is, the further back in time we're seeing it. The sun is a star, a massive ball of hot gas, primarily hydrogen and helium, held together by its own gravity. It contains about 99.86% of all the mass in our solar system. Everything else, all the planets, moons, asteroids, comets combined, make up only about 0.14% of the solar system's total mass. The sun is, by far, the dominant object in our solar system. At its core, deep in the center, the temperature reaches about 27 million degrees Fahrenheit, or 15 million degrees Celsius. At these incredible temperatures, nuclear fusion occurs. This is the process that powers the sun. Hydrogen atoms are fused together to form helium. In this process, a tiny amount of mass is converted into energy. The amount of mass converted is incredibly small, but the energy released is enormous. Einstein's famous equation, E equals mc squared, tells us that even a tiny amount of mass equals a huge amount of energy. Every second, the sun converts about 600 million tons of hydrogen into 596 million tons of helium. That means about 4 million tons of matter are converted into pure energy every single second. That energy radiates outward from the core, but it doesn't travel in a straight line. The sun is incredibly dense. The energy, in the form of photons, bounces around inside and colliding with atoms, being absorbed and re-emitted over and over again, A single photon, produced in the core, might take hundreds of thousands of years to work its way to the surface. It zigzags through the interior, bouncing randomly, in what scientists call a random walk, but eventually it reaches the surface. At the surface, the temperature is much cooler, about 10,000 degrees Fahrenheit, or 5,500 degrees Celsius, still incredibly hot by our standards, but much cooler than the core. From the surface, the energy is finally released into space as light and heat, streaming outward in all directions. 8 minutes and 20 seconds later, a tiny fraction of that energy reaches Earth. And that energy and that light is what makes life possible on our planet. It warms our atmosphere, it drives our weather, it provides energy for plants. Through photosynthesis, plants use sunlight to convert carbon dioxide and water into sugar and oxygen. That oxygen is what we breathe, and that sugar is the base of the food chain that supports all life on Earth. Without the sun, Earth would be a frozen, lifeless world. Dark and cold, the average surface temperature would be around -400 degrees Fahrenheit. No liquid water, no atmosphere as we know it, no life. The sun is essential, not just for warmth and light, but for our very existence. The sun has been shining for about 4.6 billion years, and it will continue for another 5 billion years or so. Right now, the sun is in what we call the main sequence. It's in a stable phase, converting hydrogen to helium in its core, but eventually the hydrogen in the core will run out. When that happens, the sun will change. It will begin to fuse helium into heavier elements. As it does, it will expand, growing larger and larger. It will become a red giant star, so large that it might engulf the inner planets, including possibly Earth. The outer layers of the sun will drift off into space, forming a beautiful shell called a planetary nebula. At the center, what remains of the sun will collapse, forming a white dwarf. A white dwarf is incredibly dense, about the size of Earth, but with about half the mass of the sun. A teaspoon of white dwarf material would weigh as much as an elephant. The white dwarf will slowly cool over billions of years, eventually becoming a black dwarf, a cold, dark remnant. But that's far in the future, billions of years from now. For now, the sun is stable, reliable, providing the energy we need. The sun also has weather, not weather as we know it, but complex patterns in its atmosphere. Sunspots are dark areas on the sun's surface. They're cooler than the surrounding areas, which is why they appear dark. Sunspots are caused by magnetic fields. The sun has a powerful magnetic field that gets twisted and tangled as different parts of the sun rotate at different speeds. Where the magnetic field breaks through the surface, it can suppress the flow of heat from below, creating cooler regions, sunspots. These magnetic fields can also produce solar flares, sudden, violent releases of energy. Solar flares can release as much energy as billions of nuclear bombs. They send streams of charged particles out into space. If those particles reach Earth, they can interact with our magnetic field, creating beautiful auroras, the northern and southern lights. But they can also disrupt satellites and power grids and communication systems. The sun goes through cycles. About every 11 years, the number of sunspots increases, reaches a maximum, and then decreases again. Right now, we're approaching the next solar maximum. We'll see more sunspots, more solar flares, more auroras. The sun is also surrounded by a corona, a vast atmosphere of extremely hot gas, extending millions of miles into space. During a total solar eclipse, when the moon blocks the bright disk of the sun, you can see the corona, a beautiful pearly white glow surrounding the darkened sun. The corona is incredibly hot, several million degrees, even hotter than the sun's surface. We still don't fully understand why the corona is so hot. It's one of the mysteries of solar physics. From the corona flows the solar wind, a constant stream of charged particles flowing outward from the sun at speeds of hundreds of miles per second. The solar wind fills the entire solar system. It interacts with the magnetic fields of planets. It pushes on comets, creating their tails. Eventually, far from the sun, the solar wind slows down and stops. That boundary, where the solar wind meets interstellar space, is called the heliopause. The Voyager spacecraft, and launched in 1977, have both crossed the heliopause. They're now in interstellar space, the first human-made objects to leave the solar system. The Sun is our star, our source of light and warmth. The center of our solar system, everything in our solar system, orbits the Sun, held in place by its gravity. Let's continue our gentle journey outward through our solar system. Let's visit the planets. Let's explore the inner solar system, the region where the rocky planets orbit. Mercury, the closest planet to the Sun, orbits at about 0.4 AU, roughly 36 million miles from the Sun. Mercury is small, only slightly larger than our Moon. Its diameter is about 3,000 miles or 4,800 kilometers. Mercury has almost no atmosphere, just a thin layer of atoms temporarily captured from the solar wind. Without an atmosphere to regulate temperature, Mercury experiences extreme temperature swings. During the day, when the Sun is overhead, the surface temperature can reach 830 degrees Fahrenheit or 430 degrees Celsius, hot enough to melt lead. At night, without an atmosphere to hold in the heat, the temperature plummets to minus 290 degrees Fahrenheit or minus 180 degrees Celsius. That's a temperature swing of over 1,100 degrees, the most extreme in the solar system. Mercury's surface is heavily cratered. It looks similar to our Moon, covered with the scars of billions of years of asteroid and comet impacts. There are also long cliffs called scarps. These formed when Mercury's interior cooled and contracted, causing the surface to wrinkle like a dried apple. Mercury has a large iron core. It makes up about 60% of the planet's volume. This large core gives Mercury a magnetic field. Weak compared to Earth's, but still present, Mercury orbits the Sun once every 88 Earth days, but it rotates very slowly, once every 59 Earth days. This means that on Mercury, a day from sunrise to sunrise lasts 176 Earth days. 2 Mercurian years equal 3 Mercurian days, a very unusual situation. Mercury is a harsh world, baked by the Sun on one side, frozen in darkness on the other. Not a pleasant place for humans, but fascinating to study. Venus, our neighboring planet, orbits at about 0.7 AU, or 67 million miles from the Sun. Venus is almost the same size as Earth. Its diameter is about 7,500 miles, or 12,000 kilometers. For that reason, Venus is sometimes called Earth's sister planet. But Venus is very different from Earth. Its atmosphere is incredibly thick, composed mostly of carbon dioxide, with clouds of sulfuric acid. The atmospheric pressure at the surface is about 90 times greater than Earth's pressure. That's equivalent to being 3,000 feet underwater in Earth's oceans. The thick atmosphere creates a runaway greenhouse effect. Heat from the Sun gets trapped. The surface temperature is about 900 degrees Fahrenheit or 470 degrees Celsius. That's hot enough to melt lead, hot enough to make the surface glow faintly red. Venus is the hottest planet in the solar system, even hotter than Mercury. Despite being farther from the Sun, the thick clouds completely hide the surface from view. If you stood on Venus, you wouldn't be able to see the Sun, just a dim, reddish glow filtering through the clouds. Venus is also covered in volcanoes, thousands of them. Some may still be active, though we're not certain. There are vast lava plains, mountain ranges, impact craters. The surface is dry, no liquid water, no rivers, no oceans, just hot rock and a crushing atmosphere. Venus rotates very slowly and in the opposite direction compared to most planets. One day on Venus, from sunrise to sunrise, lasts about 243 Earth days, longer than a Venusian year, which is only 225 Earth days. So on Venus, a day is longer than a year. Another unusual situation: why does Venus rotate backward? We're not sure. Perhaps a massive collision early in its history knocked it over. Venus is a hellish world, beautiful from a distance, with its bright cloud-covered appearance, but deadly up close. Despite this, Venus may have been more Earth-like in the past. Billions of years ago, it might have had oceans, a more moderate climate, but something went wrong. The greenhouse effect and spiraled out of control. The oceans evaporated, the water was lost to space, and Venus became the inferno it is today. Then comes Earth, at 1 AU, as we already know, our blue planet, with its oceans, its atmosphere, its life. From space, Earth appears as a brilliant blue and white sphere. The blue is the oceans, the white is clouds. You can see the brown and green of continents, the white of ice caps at the poles. Earth is unique in our solar system, the only planet with liquid water on its surface, the only planet where life thrives. We've already explored Earth, so let's continue outward. Mars, the red planet, orbits at about 1.5 AU, or roughly 142 million miles from the Sun. Mars is smaller than Earth, about half the diameter, with about 1/10 the mass. Its thin atmosphere is mostly carbon dioxide. The surface pressure is less than 1% of Earth's. If you stood on Mars and without a spacesuit, your blood would boil. The pressure is so low that liquid water cannot exist. Mars is cold. Average surface temperature is about -80 degrees Fahrenheit or -60 degrees Celsius. At the equator during summer, temperatures can reach 70 degrees Fahrenheit during the day, but at night, they plummet to -100 degrees. Mars gets its red color from iron oxide, rust. The surface is covered with it. The soil is red. The rocks are red. Even the sky has a reddish tinge from dust in the atmosphere. Mars has seasons, like Earth, because its axis is tilted about 25 degrees. It has polar ice caps that grow and shrink with the seasons, made of frozen water and frozen carbon dioxide, dry ice. Mars has the largest volcano in the solar system, Olympus Mons. It's about 16 miles high, nearly 3 times the height of Mount Everest. At its base, Olympus Mons is about 375 miles across, about the size of Arizona. It's a shield volcano, similar to the volcanoes in Hawaii, built up over millions of years by lava flows. Olympus Mons is probably extinct now, but in the past, it was active. Mars also has a giant canyon system, Valles Marineris. It's about 2,500 miles long, about 4 miles deep, and up to 125 miles wide in places. If it were on Earth, it would stretch from New York to Los Angeles. Valles Marineris dwarfs the Grand Canyon. It's one of the largest canyons in the solar system. Mars has ancient river channels, dry now, but they show that liquid water once flowed on the surface, billions of years ago. Mars may have been warmer. It may have had a thicker atmosphere, liquid water on the surface, perhaps even life. Today, Mars is dry and cold, but we're still searching for signs of past life. We've sent many spacecraft to Mars, rovers that have explored its surface, searching for organic molecules, for fossils, for any indication that life once existed. So far, we haven't found definitive evidence, but we're still looking. Mars represents possibility, the possibility that life might exist or might have existed elsewhere in our solar system. It's the most Earth-like planet we know of, and it's close enough that we might visit it within our lifetimes. Some people dream of establishing colonies on Mars, making it a second home for humanity. It would be difficult. The environment is harsh, but perhaps someday humans will walk on Mars. These 4 planets, Mercury, Venus, Earth, and Mars, are called the inner planets, or the terrestrial planets. They have solid, rocky surfaces. They're relatively small. They orbit close to the Sun. The distances between them are already vast, by human standards, but we're just getting started. Beyond Mars, there's a gap, a region of space, filled with asteroids. This is called the asteroid belt. And beyond that, we enter the realm of the giant planets. Let's continue our journey. Between Mars and Jupiter, there's a region of space called the asteroid belt. It contains millions of asteroids, small rocky bodies orbiting the Sun. The asteroids range in size, from tiny pebbles to objects hundreds of miles across. The largest asteroid, Ceres, is about 590 miles in diameter. It's so large that it's classified as a dwarf planet. Ceres is almost round. It has enough gravity to pull itself into a spherical shape. It may even have a subsurface ocean of liquid water, kept warm by radioactive decay in its interior. The asteroid belt exists between about 2 AU and 3.2 AU from the Sun. That's roughly 186 million miles to 298 million miles from the Sun. The asteroid belt is often depicted in movies as a dense field of rocks, where spacecraft must carefully navigate and to avoid collisions. But in reality, the asteroid belt is mostly empty space. The asteroids are spread out over an enormous volume. The average distance between asteroids is hundreds of thousands of miles. If you were flying through the asteroid belt, you likely wouldn't see any asteroids at all, unless you were specifically looking for them. The total mass of all the asteroids combined is only about 4% of the mass of the Moon, so the asteroid belt is really quite sparse. The asteroids are remnants from the early solar system. When planets were forming 4.5 billion years ago, most of the material in this region was prevented from coming together by Jupiter's gravity. Jupiter is so massive that its gravitational influence stirred up the asteroid belt, preventing the asteroids from colliding and sticking together to form a planet. So instead of a planet, we have millions of small objects orbiting the Sun, colliding occasionally, breaking into smaller pieces. Some asteroids are solid rock, others are made of iron and nickel, and some are mixtures of rock and ice. Occasionally, an asteroid's orbit is disturbed, perhaps by a collision or by Jupiter's gravity, and it might end up on a path toward the inner solar system, toward Earth. This has happened many times throughout Earth's history. Asteroids have struck Earth. About 66 million years ago, an asteroid about 6 miles across struck what is now Mexico. The impact was catastrophic. It released as much energy as billions of nuclear bombs. It threw dust and debris high into the atmosphere, blocking sunlight, causing global temperatures to plummet. The dinosaurs, along with about 75% of all species on Earth, went extinct. That impact changed the course of life on Earth. It ended the age of dinosaurs and opened the way for mammals to diversify, eventually leading to us. Asteroid impacts are rare, but they happen, and they can have enormous consequences. That's why we keep watch on asteroids, tracking their orbits, looking for any that might pose a threat to Earth. Now, let's continue beyond the asteroid belt. Let's visit the largest planet in our solar system, Jupiter. Jupiter orbits at about 5.2 AU, roughly 484 million miles from the Sun. Jupiter is massive. It's more than twice as massive as all the other planets combined. You could fit over 1,300 Earths inside Jupiter. Its diameter is about 87,000 miles, or 140,000 kilometers. If Jupiter were hollow, you could fit about 11 Earths, side by side, across its diameter. Jupiter is what we call a gas giant. It doesn't have a solid surface, like Earth. Instead, it's composed mostly of hydrogen and helium, the same elements that make up the Sun. If you could somehow descend into Jupiter's atmosphere, you'd pass through layers of clouds, deeper and deeper. The pressure would increase, the temperature would rise. Eventually, perhaps a few thousand miles down, the hydrogen would become so compressed that it would act like a liquid metal. At the very center, there might be a solid core, made of rock and ice, about the size of Earth, but we're not certain. The pressure at Jupiter's center is estimated to be millions of times Earth's atmospheric pressure. The temperature, perhaps 40,000 degrees Fahrenheit. What we do know is that Jupiter is beautiful. Its atmosphere is marked by colorful bands, stripes of different colored clouds, swirling in complex patterns. These bands are created by strong winds, blowing in opposite directions at different latitudes. Near the equator, winds blow eastward at speeds up to 335 miles per hour. At higher latitudes, winds blow westward. The different colored bands are caused by different chemicals in the atmosphere and by different temperatures. The lighter bands, called zones, are regions of rising gas, cooler and higher in the atmosphere. The darker bands, called belts, are regions of sinking gas, warmer and lower in the atmosphere. The most famous feature on Jupiter is the Great Red Spot. It's a massive storm, larger than Earth, that has been raging for at least 300 years. We first observed it in the 1600s, and it's still there today. The Great Red Spot is an anticyclone, a high-pressure system. Winds circulate around it. At speeds up to 400 miles per hour. Why is it red? We're not entirely sure. It might be due to organic compounds being brought up from deeper in the atmosphere and then altered by ultraviolet light from the sun. The Great Red Spot is slowly shrinking. 100 years ago, and it was twice as large as it is now. We don't know if it will continue to shrink, or if it will stabilize, or perhaps even grow again. Jupiter rotates very quickly. A day on Jupiter is only about 10 hours long. This rapid rotation causes Jupiter to bulge at the equator. It's not a perfect sphere, but slightly flattened. Jupiter has a powerful magnetic field, much stronger than Earth's. The magnetic field traps charged particles from the solar wind, creating intense radiation belts around the planet. These radiation belts are so strong that they would be lethal to humans and damaging to spacecraft. Jupiter also has many moons, at least 79, and that we've discovered so far. 4 of them, Io, Europa, Ganymede, and Callisto, are large moons, visible even through small telescopes. These 4 moons were discovered by Galileo Galilei in 1610. It was a revolutionary discovery because it showed that not everything in the solar system orbits Earth. The 4 Galilean moons are fascinating worlds. Io is the most volcanically active body in the solar system. Its surface is constantly being resurfaced by volcanic eruptions. Io has hundreds of active volcanoes. Some of them shoot lava plumes hundreds of miles into space. The volcanic activity is caused by tidal heating. Jupiter's gravity and the gravity of the other moons squeeze and stretch Io as it orbits, generating heat through friction. Europa is covered in ice, a smooth white surface with few craters. Beneath that ice, there's likely a global ocean of liquid water, perhaps 60 miles deep. The ice is constantly cracking and shifting, creating a complex pattern of lines and ridges. Europa's ocean is kept warm by tidal heating, just like Io, and where there's liquid water and a source of energy, there's the possibility of life. Europa is one of the most promising places in the solar system to search for life beyond Earth. Ganymede is the largest moon in the solar system, even larger than the planet Mercury. It has its own magnetic field, the only moon that does. Its surface is a mix of dark, heavily cratered terrain and lighter, younger terrain with grooves and ridges. Ganymede may also have a subsurface ocean beneath several layers of ice. Callisto is the most heavily cratered object in the solar system. Its surface is ancient, unchanged for billions of years. Callisto may also have a subsurface ocean deep beneath its icy crust. Jupiter and its moons form a miniature solar system, with Jupiter as the sun and the moons orbiting around it. Despite being far from the sun, Jupiter is a fascinating world, full of mysteries. Light from the sun takes about 43 minutes to reach Jupiter. Now, let's continue our journey. Let's visit the next giant planet, Saturn. Saturn, the beautiful ringed planet, orbits at about 9.5 AU, or roughly 886 million miles from the Sun. Saturn is also a gas giant, similar to Jupiter, but slightly smaller. Its diameter is about 72,000 miles, or 116,000 kilometers. You could fit about 9 Earths, side by side, across Saturn's diameter. Like Jupiter, Saturn is composed mostly of hydrogen and helium. It doesn't have a solid surface. In fact, Saturn is the least dense planet in the solar system. Its average density is less than water. If you could find an ocean large enough, Saturn would float. But Saturn is most famous for its rings. These rings were spectacular. They extend outward for hundreds of thousands of miles, but they're incredibly thin, only about 30 feet thick in most places. If you made a scale model where the rings were as thin as a sheet of paper, they would be more than half a mile across. The rings were made of countless pieces of ice and rock, ranging in size from tiny grains to house-sized boulders. Each piece orbits Saturn independently, following its own path. From a distance, the rings look solid, but up close you'd see that they're made of individual particles. The rings are divided into several sections, with gaps between them. The largest gap, called the Cassini division, is about 3,000 miles wide. It's caused by the gravitational influence of Saturn's moon Mimas. Particles in the Cassini division orbit Saturn at a rate that's in resonance with Mimas's orbit. This resonance causes the particles to be pulled out over time, creating the gap. The rings are surprisingly young. Scientists think they formed perhaps only a few 100 million years ago. They might be the remnants of a moon that was destroyed, perhaps by a collision or torn apart by Saturn's gravity. Eventually, the rings will disappear. The particles will slowly spiral inward, falling into Saturn, or outward, escaping into space. In a few 100 million years, Saturn might be ringless, but for now, the rings are beautiful. One of the most iconic sights in the solar system. Saturn also has many moons, at least 82 that we've discovered. The largest, Titan, is bigger than the planet Mercury. Titan is fascinating. It has a thick atmosphere, thicker than Earth's. The atmosphere is mostly nitrogen, with some methane and other organic compounds. The surface pressure on Titan is about 1.5 times Earth's pressure. You could walk on Titan without a pressure suit. Though you'd need oxygen to breathe and protection from the cold, Titan is cold. Average surface temperature is about minus 290 degrees Fahrenheit or minus 179 degrees Celsius. At those temperatures, water ice is as hard as rock, but methane and ethane can exist as liquids, and Titan has lakes and seas of liquid methane and ethane. It's the only place in the solar system, besides Earth, where stable bodies of liquid exist on the surface. Titan has weather, clouds, rain, rivers, all made of methane. It has seasons. A year on Titan is about 29.5 Earth years, so each season lasts about 7 Earth years. Titan's atmosphere is hazy. You can't see the surface from space. The haze scatters light, giving Titan an orange color, but spacecraft, using radar and infrared instruments, have mapped the surface. They've found mountains, valleys, sand dunes, lakes, rivers, landscape that looks surprisingly Earth-like, except it's made of different material, and it's incredibly cold. Beneath the surface, Titan may have an ocean of liquid water mixed with ammonia, acting as antifreeze. Titan is one of the most intriguing places in the solar system and a target for future exploration. Another interesting moon is Enceladus. Enceladus is much smaller than Titan, only about 310 miles in diameter, but it's incredibly active. At its south pole there are geysers, jets of water vapor and ice particles shooting hundreds of miles into space. These geysers come from cracks in the ice, called tiger stripes. Beneath the ice, there's an ocean of liquid water. The geysers are evidence of that ocean and of heat, keeping the water liquid, like Europa. Enceladus is a promising place to search for life. Light from the sun takes about 79 minutes to travel to Saturn. Beyond Saturn, the distances grow even larger. The planets become smaller. The sunlight becomes dimmer. Uranus orbits at about 19 AU, roughly 1.8 billion miles from the Sun. Uranus is an ice giant, slightly smaller than Saturn, with a diameter of about 31,000 miles or 51,000 kilometers. It's composed mostly of water, methane, and ammonia, surrounding a small rocky core. Uranus has a very unusual feature. It's tilted on its side. Most planets rotate with their axis roughly perpendicular to their orbit, but Uranus rotates with its axis almost parallel to its orbit. Its axis is tilted about 98 degrees, so Uranus essentially rolls along like a ball as it orbits the Sun. Why is Uranus tilted this way? We think a massive collision early in its history knocked it over. Uranus is pale blue-green in color. The methane in its atmosphere absorbs red light, giving it that distinctive hue. It has faint rings, much fainter than Saturn's, discovered in 1977, and it has 27 known moons. Uranus rotates fairly quickly. A day on Uranus is about 17 hours, but a year on Uranus is about 84 Earth years. Because of its extreme tilt, Uranus has extreme seasons. For about 42 years, one pole faces the sun, in constant sunlight. Then, for the next 42 years, the other pole faces the sun, while the first pole is in constant darkness. Uranus is cold. Average temperature at the cloud tops is about minus 350 degrees Fahrenheit or minus 210 degrees Celsius. Light from the sun takes about 2 hours and 40 minutes to reach Uranus. Neptune, the furthest major planet, orbits at about 30 AU, roughly 2.8 billion miles from the sun. Neptune is similar to Uranus, another ice giant, with a diameter of about 30,000 miles, or 49,000 kilometers. Neptune is also blue, but a deeper, richer blue than Uranus, again due to methane in its atmosphere. Neptune has the strongest winds in the solar system. Winds can reach 1,200 miles per hour. Despite being the furthest planet from the sun and receiving the least sunlight, Neptune has very active weather. Scientists think that Neptune has an internal heat source, heat left over from its formation, still radiating out. That heat drives the atmospheric circulation. Neptune also has a large storm system, similar to Jupiter's Great Red Spot. It's called the Great Dark Spot. Though unlike Jupiter's storm, Neptune's storms come and go over periods of years. The Great Dark Spot, discovered by Voyager 2 in 1989, had disappeared by 1994. New storms have appeared since then. Neptune has faint rings and 14 known moons. The largest moon, Triton, is unusual. It orbits Neptune in the opposite direction. Compared to Neptune's rotation, this is called a retrograde orbit, and it suggests that Triton wasn't formed along with Neptune. Instead, Triton was likely captured, perhaps from the Kuiper Belt. Triton is cold. Average surface temperature is about minus 390 degrees Fahrenheit or minus 235 degrees Celsius. It's one of the coldest objects in the solar system. Despite the cold, Triton is geologically active. It has geysers, shooting nitrogen gas several miles into space. Light from the sun takes over 4 hours to reach Neptune. These outer planets, Jupiter, Saturn, Uranus, and Neptune, are very different from Earth. They're enormous, mostly gas and liquid, with no solid surfaces, but they're fascinating. Each one unique, with complex atmospheres, beautiful features, and intriguing moons. Now, let's continue outward, beyond Neptune, to the edge of our solar system. Beyond Neptune, the solar system doesn't end. It continues in for a vast distance. Out here, the sun's light is incredibly faint. The temperature is incredibly cold. This is the realm of ice and darkness. Pluto, once considered the 9th planet, now classified as a dwarf planet, orbits at about 39 AU, or roughly 3.7 billion miles from the sun. Pluto is small, smaller than our moon, with a diameter of only about 1,400 miles, or 2,300 kilometers. Pluto is cold, very cold. Average surface temperature is about minus 370 degrees Fahrenheit, or minus 223 degrees Celsius. At these temperatures, nitrogen, methane, and carbon monoxide can exist as ices on the surface. Pluto has a thin atmosphere, made mostly of nitrogen, with traces of methane and carbon monoxide. But as Pluto moves farther from the sun in its orbit, the atmosphere freezes and falls to the surface as frost. In 2015, a spacecraft called New Horizons flew past Pluto. After a journey of 9.5 years, it sent back incredible images. Pluto is far more complex than anyone expected. It has mountains made of water ice, as hard as rock in the extreme cold. Some of these mountains are 3.5 miles high. Pluto has plains of frozen nitrogen, smooth and white, with a texture that looks almost like mud. These plains, called Sputnik planitia, form a large heart-shaped region on Pluto's surface. The plains are geologically young, less than 100 million years old. This suggests that Pluto is still active. Heat from its interior is still reshaping the surface. Pluto also has dark reddish regions. The color comes from organic molecules called tholins, formed when ultraviolet light from the sun breaks apart methane and nitrogen molecules, which then recombine into complex compounds. Pluto has 5 known moons. The largest, Charon's, is so big compared to Pluto that they really orbit each other. A binary system. Charon is about half the size of Pluto. Its diameter is about 750 miles. Pluto and Charon are tidally locked. They always show the same face to each other. If you stood on Pluto, Charon would hang in the sky, never moving, always in the same position. Pluto was discovered in 1930, and for 76 years it was considered the 9th planet. But in 2006, astronomers decided to redefine what it means to be a planet. To be a planet, an object must orbit the sun, have enough mass to be round, and have cleared its orbit of other debris. Pluto meets the first 2 criteria, but not the third. Pluto's orbit crosses Neptune's orbit, and the region around Pluto is filled with other objects. So Pluto was reclassified as a dwarf planet. There are other dwarf planets in the outer solar system. Eris G is about the same size as Pluto. It orbits at about 68 AU from the Sun. Makemake and Haumea are also dwarf planets, orbiting even farther out. These objects are part of the Kuiper Belt. The Kuiper Belt is a region of icy bodies, extending from about 30 AU to about 50 AU from the Sun. It's similar to the asteroid belt, but much larger and made of ice rather than rock. The Kuiper Belt contains thousands of objects, maybe hundreds of thousands, ranging from small chunks of ice to dwarf planets. The objects in the Kuiper Belt are remnants from the formation of the solar system, leftover building blocks that never came together to form planets. They're pristine, unchanged for billions of years. Studying them gives us clues about what the early solar system was like. Beyond the Kuiper Belt, there's the scattered disk. The scattered disk is another region of icy bodies, but with highly elliptical orbits. These objects were likely scattered outward by gravitational interactions with Neptune early in the solar system's history. Some scattered disk objects travel very far from the Sun, perhaps 100 AU or more, and beyond that, far, far beyond, there's the Oort cloud. The Oort cloud is a vast spherical shell of icy objects that surrounds the entire solar system. It's not directly observed, we've never seen it, but we infer its existence from the orbits of long-period comets. Long-period comets are comets that take hundreds and or even thousands of years to orbit the Sun. They come from random directions, not from the plane of the solar system. This suggests that there's a spherical cloud of comets surrounding the solar system. The Oort cloud is thought to begin at about 2,000 AU from the Sun and extend, potentially, as far as 100,000 AU. That's about 1.6 light years. 1.6 light years, let that sink in. A light year, remember, is the distance light travels in 1 year, about 6 trillion miles, or 9.5 trillion kilometers. So the outer edge of the Oort cloud is potentially about 10 trillion miles from the Sun. The Oort cloud is thought to contain billions, perhaps trillions, of icy objects. Most of them are very small, chunks of ice, a few miles across. They orbit the Sun very slowly, taking millions of years to complete one orbit. They're so far from the Sun that they're barely held by its gravity. Occasionally, one of these objects gets disturbed, perhaps by the gravity of a passing star. Its orbit changes, and it falls inward toward the Sun. As it approaches, the Sun's heat causes the ice to vaporize, forming a glowing coma and a beautiful tail. We see it as a comet. Comets have fascinated humans for thousands of years. They were seen as omens, harbingers of change, Now we know they're just chunks of ice, visitors from the distant reaches of our solar system. The Oort cloud represents the true edge of the sun's influence, the boundary of our solar system. Beyond that is interstellar space, the space between stars, and it's vast, incredibly vast. The nearest star to our sun, Proxima Centauri, is about 4.2 light-years away. That's about 270,000 AU, about 2.7 times. The distance to the outer edge of the Oort cloud, the space between stars, and is mostly empty. A few stray atoms of hydrogen, here and there, but essentially nothing. Just vast, quiet darkness. Let's take a moment to appreciate what we've covered so far. We started on Earth, 8,000 miles in diameter. We traveled to the Moon, 240,000 miles away. We visited the Sun, 93 million miles away. We explored the inner planets, Mercury, Venus, Mars. We crossed the asteroid belt. We visited the giant planets, Jupiter, Saturn, Uranus, Neptune. We ventured beyond to Pluto and the Kuiper belt, and we've reached the Oort cloud, nearly 10 trillion miles from the Sun. That's the extent of our solar system. And all of this is still just our neighborhood. We haven't even left home yet. The distances to the stars dwarf everything we've discussed so far. Let's continue our journey. Let's step outside our solar system and venture into the galaxy. Chapter 9. The nearest stars, 96 Q108 hour. The nearest star to our Sun is called Proxima Centauri. It's part of a 3-star system called Alpha Centauri. Proxima Centauri is about 4.2 light-years away from us. Remember, 1 light-year is about 6 trillion miles, or 9.5 trillion kilometers, so Proxima Centauri is roughly 25 trillion miles away. 25 trillion miles, that's an almost incomprehensible distance. If you could travel at the speed of light, which nothing with mass can do, it would still take you 4.2 years to reach our nearest neighboring star, the fastest spacecraft we've ever built. Voyager 1, which left Earth in 1977, travels at about 38,000 miles per hour. That's incredibly fast by human standards, but in the vastness of space, it's incredibly slow. At that speed, it would take Voyager 1 over 70,000 years. To reach Proxima Centauri, 70,000 years, that's longer than all of recorded human history. The distances between stars are vast, almost incomprehensibly vast. Let's try to visualize this using our scale model. Remember, we said that if the Sun were a basketball, Earth would be a small p, about 26 yards away. Neptune would be another small p, nearly a quarter of a mile away. On that same scale, Proxima Centauri would be another basketball, placed about 4,000 miles away. 4,000 miles, that's roughly the distance from New York to London. Imagine that. 2 basketballs representing the Sun and Proxima Centauri, separated by the width of the Atlantic Ocean, and in between, almost nothing, just empty space. That's what the space between stars is really like. The space between stars is mostly empty, almost perfectly empty. There are a few stray atoms of hydrogen here and there, on average, about 1 atom per cubic centimeter. For comparison, Earth's atmosphere at sea level contains about 25 quintillion molecules per cubic centimeter, so the space between stars is one of the best vacuums in the universe. Just vast, quiet darkness. This emptiness is one of the defining characteristics of space. It's not crowded, it's not dense, it's mostly nothing. Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun. Its diameter is only about 1/7 the diameter of the Sun, about 120,000 miles across, and it shines with only about 1/6 of 1% of the Sun's brightness. If you were standing on a planet orbiting Proxima Centauri, the star would look much dimmer than our Sun. You'd need to be much closer to receive the same amount of warmth and light. Red dwarf stars are the most common type of star in the galaxy. They make up about 70 to 80% of all stars. They're small, dim, cool, but they have one advantage: they burn their fuel very slowly. A red dwarf star can shine for trillions of years, much longer than our Sun. Our Sun will exhaust its fuel in about 10 billion years total. It's already halfway through its life, but a red dwarf could keep shining for hundreds of times longer. Long after our sun has died, red dwarf stars will still be burning. Interestingly, Proxima Centauri does have at least one. Planet Proxima Centauri b. This planet was discovered in 2016 using the radial velocity method. Scientists observed that Proxima Centauri wobbles slightly. The gravity of an orbiting planet pulls on the star, causing it to move back and forth. By measuring that wobble, scientists can detect the planet and calculate its mass and orbit. Proxima Centauri b is about the same mass as Earth, perhaps slightly larger, and it orbits in what we call the habitable zone, the region around a star, where the temperature is just right for liquid water to exist on a planet's surface. Too close to the star, and the water evaporates. Too far, and it freezes. Proxima Centauri b orbits in that sweet spot, so it's possible that it has liquid water, and maybe, just maybe, life, but we don't know yet. The planet is far too distant for us to study in detail. We can't see it directly, we only know it exists from its gravitational effect on the star. Still, it's exciting to think about. The nearest star to our sun might have a habitable planet. If we could travel there, what would we find? Would there be oceans, continents, an atmosphere? Would there be life, simple bacteria, or something more complex? We don't know, but perhaps, someday, we'll find out. There are other stars near us, relatively speaking. Barnard's star is about 6 light-years away. Another red dwarf, Wolf 359, is about 7.8 light-years away. Also a red dwarf, Lalande 21185, is about 8.3 light-years away. Sirius, the brightest star in our night sky, is about 8.6 light-years away. Sirius is actually a binary system, 2 stars orbiting each other. Sirius A is a bright white star, about twice the size of the Sun, much hotter and brighter. It's what we call an A-type main sequence star, young and hot. Sirius B is a white dwarf, a small dense star, the remnant of a star that has exhausted its fuel and collapsed. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh as much as an elephant. Sirius B is only about the size of Earth, but it contains about as much mass as the Sun. When we look at Sirius in the night sky, we're mostly seeing Sirius A. It's so bright, it outshines its companion, but with a telescope, you can see Sirius B, a tiny, faint dot, next to the brilliant Sirius A. Within about 15 light-years of the Sun, there are roughly 60 star systems. Some are single stars, like Proxima Centauri or Barnard's star. Others are binary systems, 2 stars orbiting each other like Sirius. And a few are triple systems, 3 stars, bound together by gravity. 60 star systems within 15 light-years. That might sound like a lot, but remember, we're talking about a sphere. With a radius of 15 light-years, the volume of that sphere is enormous, about 14,000 cubic light-years, and within that entire volume, there are only 60 stars. If we expand our view to within 30 light-years, we find about 350 stars. Within 50 light-years and about 1,500 stars. Within 100 light-years, about 14,000 stars. These numbers give us a sense of the density of stars in our region of the galaxy. On average, stars are separated by several light-years. Space is very, very empty. Most of the stars near us are red dwarfs, small, cool stars, much more common than stars like our Sun. Red dwarfs can burn for trillions of years, much longer than our Sun will. They're dim, hard to see. Many of them are invisible to the naked eye, but they make up the majority of stars in the galaxy. Stars like our Sun, yellow dwarf stars, are less common, but still fairly typical. Our Sun is what we call a G-type main sequence star, medium-sized, medium temperature. It will live for about 10 billion years total, and it's currently about halfway through its life. And then there are larger stars, blue giants, red giants, supergiants. These stars are rare, but spectacular. Some of them are hundreds of times larger than the Sun. Betelgeuse, a red supergiant in the constellation Orion, is about 700 times larger than the Sun. If you placed Betelgeuse where our Sun is, it would extend past the orbit of Mars. Earth would be inside the star. These giant stars burn hot and fast. They live for only a few million years, a blink of an eye, compared to the billions of years that smaller stars can live. When they die, they do so spectacularly, exploding in supernovae. A supernova releases as much energy in a few months as the Sun will release in its entire 10 billion-year lifetime. For a brief time, a supernova can outshine an entire galaxy. The explosion scatters the star's material across space, enriching the interstellar medium with heavier elements, and from that material, new stars and new planets eventually form. This is the cycle of stellar life: birth, life, death, and rebirth. Our Sun formed from such material, the remnants of stars that died billions of years ago, and someday, billions of years from now, the material from our Saturn will be recycled, forming new stars, new worlds. The cycle continues. All of these stars, the ones near us and the billions of others, are part of a massive structure, a spiral galaxy that we call the Milky Way. Let's zoom out and look at our place in the galaxy. Our Sun, along with all those neighboring stars and billions upon billions of other stars, are all part of a massive structure called the Milky Way galaxy. The Milky Way is a spiral galaxy. If you could look at it from above, from outside, it would look somewhat like a giant pinwheel, with a bright central bulge and curved arms spiraling outward. Our Sun is located about 26,000 light-years from the center of the galaxy. 26,000 light-years, that's roughly 153 quintillion miles. A quintillion is a 1 followed by 18 zeros. The numbers are getting so large now that they're almost meaningless in any practical sense. But let's continue. Our Sun orbits the center of the galaxy. Just as Earth orbits the Sun orbits the galactic center. The Sun's orbital speed is about 450,000 miles per hour. That's incredibly fast. But the galaxy is so large that even at that speed it takes about 225 million years to complete one full orbit around the galaxy. We call this a galactic year. The last time our solar system was in this same position, dinosaurs were just beginning to walk the Earth. The time before that, complex life had only recently emerged in Earth's oceans. That's how vast the Milky Way is. The Milky Way, from edge to edge, is about 100,000 light-years across. 100,000 light-years, that's about 600 quintillion miles. If we go back to our scale model, where the Sun is a basketball and Proxima Centauri is another basketball 4,000 miles away, the Milky Way galaxy, on that same scale, would be about 10 million miles across. That's about 40 times the distance from Earth to the Moon. On that scale, our entire solar system, out to Neptune, would be less than an inch across. The galaxy is also quite flat, like a disk. Its thickness, from top to bottom, is only about 1,000 light-years in most places, though it's thicker near the center, where there's a bulge. If we made a scale model, where the Milky Way is the size of the United States from coast to coast, the thickness of the disk would be only about 60 miles, so the galaxy is very flat, like a dinner plate. Our Sun is located in one of the spiral arms, called the Orion Arm, or sometimes the Orion Spur. The spiral arms are regions of higher density, where stars are more closely packed together. They're also regions of active star formation, where new stars are being born from clouds of gas and dust. The spiral arms contain many young hot blue stars. These stars are so bright that they make the spiral arms stand out. But most of the stars in the galaxy are older, cooler, dimmer stars, like our Sun. These stars are spread throughout the disk, not just in the spiral arms, the spiral structure, and is actually a density wave, not a physical structure. Stars don't stay in the spiral arms. They orbit the galactic center at their own speeds. Sometimes they pass through a spiral arm. Sometimes they're between the arms. It's like a traffic jam on a highway. Cars slow down, creating a region of higher density, but individual cars move through the jam. The spiral arms work the same way. Within the Milky Way, there are approximately 200 to 400 billion stars. That's 200 billion to 400 billion individual suns, each one, potentially, with its own system of planets. Some of these stars are much larger than our sun, some are smaller, some burn hot and blue, others glow cool and red, and scattered throughout the galaxy, mixed in between the stars, are vast clouds of gas and dust, called nebulae. These nebulae are the birthplaces of new stars. Gravity slowly pulls the gas together over millions of years, until it becomes dense enough and hot enough for nuclear fusion to begin. And then a new star is born. This process has been happening throughout the history of our galaxy for billions upon billions of years. Our sun formed this way about 4.6 billion years ago from a cloud of gas and dust that once floated in this same spiral arm. The material in that cloud came from earlier generations of stars, stars that lived and died before our sun was born. When massive stars die, they explode as supernovae, scattering their material, enriched with heavy elements, across space. That material mixes with the interstellar gas, and eventually it comes together to form new stars. Our sun contains elements created in the hearts of ancient stars: carbon, oxygen, nitrogen, iron, all forged in stellar furnaces, and within our sun, and in the planets around it, including Earth, that ancient stardust continues to exist. We are, quite literally, made of the remnants of dead stars. The Milky Way, that also has structure beyond its spiral arms. At the very center of the galaxy, there is a supermassive black hole called Sagittarius A star. This black hole has a mass about 4 million times the mass of our sun, 4 million solar masses, compressed into a region smaller than the orbit of Mercury. It sits there, at the center, pulling on all the stars in the galaxy, helping to hold everything together through gravity. A black hole is a region of space in where gravity is so strong that nothing can escape, not even light. The escape velocity, the speed you'd need to escape from a black hole, is greater than the speed of light. But since nothing can travel faster than light, nothing can escape. When a massive star runs out of fuel, it can collapse into forming a black hole. But the black hole at the center of our galaxy didn't form from a single star. It's far too massive for that. Instead, it likely formed in the early days of the galaxy, from the merger of many smaller black holes, and from gas falling into the center. Over billions of years, it grew, consuming stars and gas that ventured too close. We can't see the black hole itself because no light escapes from it, but we can see its effects. Stars near the center of the galaxy orbit at incredible speeds. Some complete an orbit around the invisible mass in just a few years. By measuring those orbits very precisely, we can calculate the mass of the black hole. Astronomers have been tracking these stars for over 20 years now, watching them orbit, the unseen monster at the center of our galaxy. It's one of the most direct pieces of evidence that supermassive black holes exist. Around the main disk of the galaxy, there's also a spherical halo. The halo is a roughly round region filled with old stars and globular clusters. Globular clusters are tight balls of hundreds of thousands of stars, all orbiting together around the center of the galaxy. These clusters are very old, some of the oldest objects in the galaxy, dating back nearly to the beginning, about 13 billion years old. When you look at a globular cluster through a telescope, it's breathtaking. Hundreds of thousands of stars packed so closely together that they form a glowing sphere. In the densest parts of a globular cluster, stars are only about 1 light-year apart. That might still sound like a lot, but remember, in our neighborhood, the nearest star is over 4 light-years away. In a globular cluster, you'd have hundreds of bright stars. In the night sky, it would never truly be dark. The Milky Way is ancient. It formed about 13.6 billion years ago, not long after the universe itself began. Since then, it's been slowly evolving. Stars being born, stars dying, gas clouds collapsing and expanding, a constant cycle of creation and destruction. And through it all, the galaxy continues to rotate. Different parts rotate at different speeds. This is called differential rotation. The inner regions rotate faster. The outer regions rotate slower. This differential rotation is what creates and maintains the spiral structure. The Milky Way is a dynamic, living system, constantly changing, constantly evolving, and we are part of it. One tiny solar system, among hundreds of billions, orbiting the center every 225 million years. Our galaxy is our home, on a larger scale. Just as Earth is our home planet, the Milky Way is our home galaxy. Now, let's explore the Milky Way in more detail. Let's take a closer look at the structure of our galaxy. The Milky Way has several distinct components. The disk, the flat, rotating part, contains most of the stars and all of the spiral arms. The disk is where active star formation occurs, where new stars are being born. Within the disk, there are different populations of stars. Young, hot, blue stars are found primarily in the spiral arms. These stars are only a few million years old. They shine brightly, but they'll burn out quickly, living for only a few million years. Older stars, like our Sun, are spread throughout the disk, not just in the spiral arms. These stars are billions of years old. They shine more dimly but they'll last much longer. The disk also contains vast amounts of gas and dust, the raw material for future stars. These clouds can be enormous, hundreds of light years across. One famous example is the Orion Nebula, a stellar nursery, about 1,500 light years away. In the Orion Nebula, we can see stars being born, right now, in real time. Through telescopes, we can see protostars, young stars, still surrounded by disks of gas and dust. Planets are probably forming in those disks, just as they did around our Sun 4.5 billion years ago. The Orion Nebula is visible to the naked eye as a faint, fuzzy patch in the constellation Orion, but through a telescope, it's spectacular. A glowing cloud illuminated by young stars. The central bulge of the Milky Way is a roughly spherical region at the center of the galaxy. It contains billions of older stars, packed closely together. The bulge is much denser than the disk. Stars are much closer together. If you lived on a planet in the central bulge, your night skies would be filled with stars, thousands of them, bright enough to cast shadows. But the central bulge also contains a lot of dust, which obscures our view. We can't see the center of the galaxy in visible light. The dust blocks it, but we can observe it in infrared light and radio waves, which pass through the dust. Using these wavelengths, astronomers have mapped the central regions of the galaxy. They've discovered not only the supermassive black hole, but also a dense cluster of stars orbiting close to it, and regions of intense star formation, despite the harsh environment near the black hole. Surrounding the disk and bulge is the galactic halo. The halo is a roughly spherical region, extending perhaps 300,000 light-years from the center, much larger than the disk itself. The halo contains globular clusters and individual old stars. These objects orbit the galactic center, but not in the plane of the disk. They orbit in all directions, some in retrograde, orbiting opposite to the disk's rotation. The halo is also where most of the galaxy's dark matter resides. Dark matter is mysterious. We can't see it. It doesn't emit light. It doesn't interact with normal matter, except through gravity, but we know it's there, because we can see its gravitational effects. The stars in the outer regions of the galaxy orbit faster than they should. Based on the visible matter alone, there must be additional mass pulling on them, and that mass is dark matter. In fact, dark matter makes up about 85% of the matter in the galaxy. Only about 15% is normal matter, the stuff we can see. We don't know what dark matter is. It might be exotic particles that we haven't discovered yet, particles that don't interact with light and barely interact with normal matter. Detecting dark matter is incredibly difficult because it's so elusive. Scientists have built detectors deep underground, shielded from cosmic rays and other radiation. They're waiting hoping for a dark matter particle to occasionally collide with a normal atom. So far, we haven't detected it directly, but we're still looking. Dark matter is one of the biggest mysteries in modern astronomy. The Milky Way also contains many different types of objects. There are young stars, still forming in nebulae, hot and bright. There are middle-aged stars, like our Sun, stable and steady. There are old stars, red giants, white dwarfs. There are binary stars, two stars orbiting each other. There are neutron stars, incredibly dense remnants of exploded stars. A neutron star is only about 12 miles in diameter, but it contains more mass than the Sun. A single teaspoon of neutron star material would weigh as much as a mountain on Earth. The density is incredible, almost beyond comprehension. Neutron stars are made almost entirely of neutrons, packed together so tightly that there's no space between them. Some neutron stars are pulsars, rapidly spinning neutron stars that emit beams of radiation, like cosmic lighthouses. As the pulsar spins, the beams sweep across space. If one of those beams points toward Earth, we see a pulse of radiation. Some pulsars spin hundreds of times per second with incredible regularity. They're some of the most precise clocks in the universe. The Milky Way also contains many black holes, not just the supermassive one at the center. Every massive star that reaches the end of its life and collapses can potentially form a black hole. It's estimated that there might be 100 million black holes in our galaxy. Most of them are isolated, invisible, just sitting in space, but some are in binary systems, orbiting a companion star, slowly pulling material from that star onto themselves. When material falls into a black hole, it heats up, emitting X-rays. That's how we can detect them. By searching for X-ray sources, astronomers have found dozens of black holes in our galaxy, and there are likely millions more that we haven't detected yet. The Milky Way is also filled with cosmic rays. Cosmic rays are high-energy particles, protons, electrons, atomic nuclei, traveling through space at nearly the speed of light. They come from supernovae, from pulsars, from the supermassive black hole at the center. Cosmic rays fill the galaxy, constantly bombarding everything, including Earth. Our atmosphere protects us. Most cosmic rays collide with air molecules high in the atmosphere, creating showers of secondary particles, but some make it through and hit the ground. You, right now, are being hit by cosmic rays, particles that traveled perhaps thousands of light years through the galaxy before reaching you. It's a reminder that we're connected to the cosmos, not separate from it. The Milky Way is our home galaxy, but it's not alone. It's part of a larger structure, a group of galaxies bound together by gravity. Let's zoom out once more and look at our cosmic neighborhood. The Milky Way is part of what astronomers call the local group. The local group is a collection of more than 50 galaxies, all relatively close to each other, bound together by gravity. The largest galaxy in the local group is the Andromeda Galaxy, also known as M31. Andromeda is about 2.5 million light-years away from us. 2.5 million light-years. That's roughly 15 sextillion miles. A sextillion is a 1, followed by 21 zeros. The distances are becoming almost abstract, so large that they lose all connection to our everyday experience. But let's continue. Andromeda is similar to the Milky Way. It's also a spiral galaxy, though it's somewhat larger, containing perhaps 1 trillion stars, about twice as many as the Milky Way. Andromeda has a diameter of about 220,000 light-years, more than twice the diameter of the Milky Way. When we look at Andromeda in the night sky, even though it's very faint, we can see it with the naked eye on a dark, clear night. It appears as a small fuzzy patch in the constellation Andromeda, but that small patch is an entire galaxy, 1 trillion stars, and the light we see left Andromeda 2.5 million years ago. We're seeing the galaxy as it was, long before humans existed on Earth, long before our earliest ancestors walked upright. Andromeda is slowly moving toward us. at about 68 miles per second. That might not sound fast, but over millions of years, it adds up. In about 4 billion years, our two galaxies will collide. Don't worry. When galaxies collide, the stars themselves almost never actually hit each other. The distances between stars were so vast that they simply pass by one another. But the gravitational interactions will be dramatic. The two galaxies will pass through each other. Stars will be flung out into intergalactic space. The supermassive black holes at the centers of both galaxies will spiral inward. Eventually, they'll merge, forming an even larger black hole. And over hundreds of millions of years, the two galaxies will merge, forming a single larger galaxy, probably an elliptical galaxy. Some astronomers have nicknamed this future galaxy Milkomeda, but that's 4 billion years in the future, long after the Sun has died. For now, Andromeda is still approaching, but we're still separate galaxies. Another notable member of the local group is the Triangulum galaxy, also known as M33. Triangulum is about 3 million light-years away. It's smaller than both the Milky Way and Andromeda, containing perhaps 40 billion stars. Triangulum is also a spiral galaxy with beautiful, well-defined spiral arms. It's visible through binoculars or a small telescope in the constellation Triangulum. There are also many smaller galaxies in the local group, dwarf galaxies, containing only a few billion stars or even just a few million. These dwarf galaxies often orbit around larger galaxies, like satellites. The Milky Way has several satellite galaxies. The Large Magellanic Cloud and the Small Magellanic Cloud are two of them. They're visible from the southern hemisphere as faint cloudy patches in the night sky. The Large Magellanic Cloud is about 160,000 light-years away. It contains about 10 billion stars. The Small Magellanic Cloud is about 200,000 light-years away. It contains about 3 billion stars. These dwarf galaxies are being slowly pulled apart out by the Milky Way's gravity. Eventually, they'll be absorbed. Their stars will become part of the Milky Way. This process is called galactic cannibalism, and it's common in the universe. Large galaxies grow by consuming smaller ones. The Milky Way has likely consumed dozens of smaller galaxies over its history. We can still see the remnants, streams of stars, stretched out across the sky. The ghosts of ancient dwarf galaxies, torn apart by tidal forces. Andromeda also has satellite galaxies, at least 14 that we've discovered. And Triangulum may be a satellite of Andromeda, or it may be an independent galaxy. We're not sure. The local group, the collection of all these galaxies, is about 10 million light-years across. 10 million light-years, that's roughly 60 sextillion miles. Within this region, these 50-plus galaxies orbit around each other, pulled together by gravity. The local group is a gravitationally bound structure, meaning that the galaxies within it are held together. They won't fly apart as the universe expands. Their mutual gravity is strong enough to keep them together. But the local group is itself part of something much larger. It's part of the Virgo supercluster. A supercluster is a massive structure made up of many galaxy groups and clusters, all loosely connected across hundreds of millions of light-years. The Virgo supercluster contains at least 100 galaxy groups and clusters, with a total of about 47,000 galaxies. The Milky Way and our local group are located near the edge of this supercluster. We're in the outskirts, not near the center. The center of the Virgo supercluster is marked by the Virgo cluster. The Virgo cluster is a dense collection of over 1,000 galaxies, located about 65 million light-years away from us. At the heart of the Virgo cluster, there's a giant elliptical galaxy called Messier 87 or M87. M87 is enormous. It contains about 1 trillion stars, and at its center there's a supermassive black hole with a mass about 6.5 billion times the mass of the Sun. In 2019, astronomers captured the first-ever image of a black hole. The black hole at the center of M87, using a network of radio telescopes spread across the entire Earth, they were able to image the shadow of the black hole. a dark circle, surrounded by a glowing ring of hot gas. It was a historic achievement, the first direct image of a black hole. The entire Virgo supercluster spans about 110 million light-years across. 110 million. Light-years, that's roughly 650 septillion miles. A septillion is a 1, followed by 24 zeros. At this scale, individual stars become meaningless. Even individual galaxies start to seem small. We're now looking at structures that contain trillions upon trillions of stars, but even this is still not the largest scale. In recent years, astronomers have discovered that the Virgo supercluster is actually just one lobe of an even larger structure called Laniakea. Laniakea is a supercluster of superclusters. It contains about 100,000 galaxies and spans roughly 520 million light-years across. The word Laniakea comes from Hawaiian and means immeasurable heaven. It's a fitting name. Within Laniakea, galaxies and galaxy clusters are all slowly flowing, moving along gravitational currents like rivers in space. They're being drawn toward a region called the Great Attractor. The Great Attractor is a gravitational anomaly, a region of space where an enormous amount of mass is pulling on everything around it. We can't see the Great Attractor directly because it lies behind the disk of our own galaxy, obscured by dust and stars, but we can measure its effect by observing how galaxies move. Entire galaxy clusters, including our own local group, are being pulled toward the Great Attractor at speeds of hundreds of miles per second and beyond. Laniakea, there are other superclusters, hundreds of them, thousands of them, each one containing hundreds of thousands of galaxies, each galaxy containing hundreds of billions of stars. And all of these structures are part of what we call the observable universe. Let's talk about that now. Let's take a moment to understand the largest structures in the universe. Galaxies are not evenly distributed throughout space. They're not scattered randomly. Instead, they cluster together, forming groups and clusters. We've already talked about the local group, our small collection of about 50 galaxies, but there are much larger clusters containing thousands of galaxies. The Virgo cluster, for example, contains over 1,000 galaxies, all within a region about 15 million light-years across. The Coma cluster contains over 1,000 galaxies, located about 300 million light-years away. The galaxies in these clusters are bound together by gravity, orbiting around a common center of mass. Between the galaxies, there's hot gas, heated to millions of degrees by the gravitational energy of the cluster. This gas emits X-rays. We can detect it using X-ray telescopes in space. The hot gas contains more mass than all the visible stars in the cluster combined. But even the hot gas and all the visible matter isn't enough to hold the cluster together. The galaxies are moving too fast. Based on the visible matter, they should fly apart, but they don't, because there's dark matter, lots of it. Dark matter makes up about 85% of the mass in galaxy clusters. We can't see it, but we can detect it through its gravitational effects, using a technique called gravitational lensing. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the path of the light is bent by the gravity of the cluster. This causes the distant galaxy in turn to appear distorted, stretched, sometimes into multiple images. By studying these distortions, astronomers can map the distribution of dark matter in the cluster, even though they can't see it directly. Galaxy clusters are the largest gravitationally bound structures in the universe, but they're not the end of the story. Clusters themselves cluster together, forming superclusters. Superclusters are vast, sprawling structures containing dozens or hundreds of galaxy clusters spanning hundreds of millions of light-years. But superclusters are not gravitationally bound. They're too large and too loosely connected. The expansion of the universe is pulling them apart. Within a supercluster, you'll find clusters, groups, and individual galaxies, all connected by filaments of galaxies, long, thin strands stretching across space. Between the filaments are voids, vast, empty regions containing very few galaxies. The structure of the universe, and on the largest scales, looks like a cosmic web, filaments and sheets of galaxies surrounding vast voids. This structure formed over billions of years as gravity pulled matter together in some regions while leaving other regions empty. The cosmic web is one of the most striking features of the universe. Laniakea, our home supercluster, is just one region of this web, a collection of galaxy clusters flowing together toward the Great Attractor. But the Great Attractor isn't the end. It's part of an even larger structure called the Shapley supercluster. The Shapley supercluster is one of the most massive structures in the nearby universe, containing about 8,000 galaxies. Located about 650 million light-years away, its gravity is so strong that it influences the motion of galaxies across hundreds of millions of light-years. Even our local group is being pulled, very slightly, toward the Shapley supercluster. These massive structures, superclusters and galaxy filaments, are the largest things in the universe, but they're not uniform, not evenly spaced. The universe has texture, structure. Some regions are dense, filled with galaxies. Others are nearly empty. This structure tells us something important about the early universe. It tells us that the universe wasn't perfectly smooth. There were tiny variations in density, regions that were slightly denser than average, and gravity amplified those variations. Dense regions pulled in more matter, becoming denser still. Over billions of years, those tiny variations grew into the galaxies and clusters we see today. We can still see the remnants of those early variations in something called the cosmic microwave background. The cosmic microwave background is the afterglow of the Big Bang, light from when the universe was only 380,000 years old. At that time, the universe was filled with hot plasma, too hot for atoms to form. But as the universe expanded, it cooled. Eventually, it became cool enough for atoms to form. When that happened, light was able to travel freely, no longer scattered by plasma. That light has been traveling through space ever since, for over 13 billion years. And as the universe expanded, the light was stretched, shifted to longer wavelengths. Today, that light reaches us as microwaves, very cold radiation. Only about 3 degrees above absolute zero, the cosmic microwave background and fills the entire sky, coming from all directions, using sensitive instruments. Astronomers have mapped it with incredible precision, and they've found tiny variations, regions that are slightly warmer or slightly cooler. These variations are the seeds of structure, the tiny differences in density that eventually grew into galaxies. The cosmic microwave background is one of the most important pieces of evidence for the Big Bang theory. It shows us that the universe was once very hot, very dense, and expanding. Now, let's talk about the observable universe as a whole, the limits of what we can see, and what lies beyond. The observable universe is the portion of the universe that we can see, or potentially detect, from Earth. It's limited, not because the universe ends, but because light has only had a certain amount of time to reach us. The universe, according to our best measurements, is about 13.8 billion years old. It began in an event we call the Big Bang. At that moment, all the matter and energy in the universe was compressed into an incredibly hot, incredibly dense state. And then it expanded, rapidly, violently. It's still expanding today. Because the universe is 13.8 billion years old, you might think the furthest we can possibly see is 13.8 billion light-years. But no, it's more complicated than that. The universe has been expanding this entire time, so objects that were far away, when they emitted light, have moved even further away, while that light was traveling toward us. When we account for this expansion, the radius of the observable universe is about 46.5 billion light-years. 46.5 billion light-years. That's the distance from Earth to the edge of what we can observe in any direction. The diameter of the observable universe from one edge to the other, passing through Earth, is about 93 billion light-years. 93 billion light-years. That's roughly 550 octillion miles. An octillion is a 1, followed by 27 zeros. This is, as far as we can see, this is the boundary of the observable universe. Beyond that boundary, there is almost certainly more universe, possibly infinitely more. But that region is beyond our ability to observe. The light from those distant places hasn't had time to reach us yet, and because the universe is expanding and that expansion is accelerating, some of that light never will reach us. Within the observable universe, we can estimate how many galaxies there are. Current estimates suggest there are about 200 billion galaxies in the observable universe. Some astronomers think the number might be even higher, perhaps 2 trillion galaxies. Each galaxy contains, on average, about 100 billion stars, so the total number of stars in the observable universe is approximately 1 septillion. That's a 1, followed by 24 zeros, or written out, 1,000 billion billion billion. 1 septillion stars, each one a sun, many of them with planets, and all of this exists within a sphere, 93 billion light-years across. Let's pause now and consider what this means. The observable universe is unimaginably vast. The distances involved are so large that they lose all meaning in terms of human experience. Light, the fastest thing in the universe and traveling at 186,000 miles per second, would take 93 billion years to cross from one side of the observable universe to the other. Except it can't, because the universe is expanding. By the time light traveled from one edge to where the other edge was, the universe would have expanded so much that the edge would be even further away. In fact, there are galaxies we can see now that we will never be able to reach, even if we could travel at the speed of light, because they're moving away from us, faster than light can travel toward them. This doesn't violate the laws of physics, because nothing is actually moving through space faster than light. Rather, space itself is expanding, carrying things along with it. The observable universe is also remarkably uniform. When we look in any direction, at the largest scales, the universe looks roughly the same. Galaxies are distributed, more or less evenly, throughout space. There are denser regions and emptier regions, but on average, looking at scales of hundreds of millions of light-years, the universe is homogeneous. This is called the cosmological principle, the idea that, on large scale, the universe is the same everywhere. There's no center to the universe, no special location. Every point in space is more or less equivalent to every other point. When we say the universe is expanding, we don't mean it's expanding into something. There's no edge, no boundary, no outside. Instead, every point in space is moving away from every other point. The fabric of space itself is stretching. Imagine the surface of a balloon. As you inflate the balloon, every point on the surface moves away from every other point. But there's no center on the surface, no point that's special. The universe is like that, except in 3 dimensions rather than 2. This might seem strange. It is strange, but it's what all our observations tell us. The expansion of the universe was first discovered by Edwin Hubble in 1929. He observed that distant galaxies were moving away from us, and the further away they were, the faster they were receding. This relationship between distance and speed is now called Hubble's law. It told us that the universe was not static, but dynamic, changing, expanding. Since then, we've measured this expansion with increasing precision. We've also discovered that the expansion is accelerating. Galaxies that are very far away are moving away from us, faster and faster. Over time, we don't fully understand why. We attribute it to something called dark energy, a mysterious force that seems to permeate all of space, pushing things apart. Dark energy makes up about 68% of all the energy in the universe. Dark matter, another mysterious substance, makes up about 27%. And ordinary matter, the stuff that makes up stars, planets, you and me, makes up only about 5% of the universe. Most of the universe is invisible to us. We can only detect it indirectly, so as through its effects on the things we can see. This is humbling. Even with all our technology, all our knowledge, we understand only a small fraction of what the universe is made of. But we keep observing, keep measuring, keep learning, and slowly our picture of the universe becomes clearer. The observable universe is vast, but it might be only a tiny fraction of the total universe. If the universe is infinite, and some theories suggest it might be, then the observable universe is just an infinitesimal bubble, a tiny region where light has had time to reach us. Beyond that, more universe, more galaxies, more stars, perhaps forever. We don't know. We may never know, but we can marvel at what we can see and what we've learned. Now, let's take a moment to reflect on all of this. So, how big is the universe? Really, the observable universe is 93 billion light-years across. That's as far as we can see. Beyond that, the universe might go on forever, or it might curve back on itself. We don't know. What we do know is that the universe is vastly, almost incomprehensibly, larger than anything in our everyday experience. Earth, our home, is tiny, a small, rocky planet, orbiting an ordinary star in an ordinary spiral arm of an ordinary galaxy. Our sun is one star among hundreds of billions in the Milky Way. The Milky Way is one galaxy among trillions in the observable universe. And yet, here we are, conscious, aware, able to contemplate all of this. It's remarkable when you think about it. We are made of atoms, forged in the hearts of ancient stars. Carbon, oxygen, nitrogen, iron, calcium, phosphorus, all the elements that make up our bodies were created billions of years ago in stars that have long since died. Those stars lived their lives, fused lighter elements into heavier ones, and then, at the end of their lives, exploded, scattering those elements into space. Over time, those elements came together in clouds of gas and dust, forming new stars, new planets, and eventually, on at least one of those planets, those elements came together in just the right way to form life. Simple at first, single-celled organisms, but over billions of years, life became more complex, more diverse, and eventually, conscious we are quite literally made of stardust, the remnants of ancient stars that died long before Earth was born. And now, we can look back at the universe that created us and try to understand it. This is both humbling and empowering. Humbling because we realize how small we are, how brief our lives are compared to the age and scale of the cosmos. A human lifetime is about 80 years. The universe is 13.8 billion years old. If the entire history of the universe were compressed into a single year, humans would appear in the last few seconds before midnight on December 31st. We are newcomers, recent arrivals, and Earth, our home, is a tiny speck in a vast, vast universe. But this realization is also empowering, because despite our size, despite our brief existence, we can understand these things. We can measure distances spanning billions of light years. We can peer back in time to the early universe. We can unravel the laws of physics that govern everything from the smallest particles to the largest structures. The universe is vast, but it's not beyond our comprehension. Every number we've discussed, every distance, every scale, was measured by humans, calculated by humans, understood by humans. With nothing but our minds and our tools, we've mapped the cosmos. We've sent spacecraft to other planets. We've landed robots on Mars. We've flown past Pluto and beyond, into interstellar space. We've built telescopes that can see galaxies so far away. Their light has been traveling for billions of years before reaching us. We've learned to read that light, to understand what those distant galaxies are made of, how fast they're moving, how old they are. This is one of humanity's greatest achievements, our ability to understand the universe we live in, and we're still learning, still discovering. Every year, astronomers find new things, new galaxies, new planets, new phenomena. that challenge our understanding. The universe is full of mysteries, questions we haven't answered yet. What is dark matter? What is dark energy? Are there other universes beyond our own? Is there life elsewhere in the cosmos, on other planets, orbiting other stars, in other galaxies? We don't know yet, but we're looking, searching, and perhaps, someday, we'll find answers. For now, we can simply marvel at the immensity of it all. The universe is big, unimaginably big, and yet it all started 13.8 billion years ago from a single point, infinitely small, infinitely dense, infinitely hot. And from that beginning, everything emerged. Space, time, matter, energy. The universe expanded, cooled, atoms formed, stars formed, galaxies formed, planets formed. And on at least one of those planets, life arose. Life that could think, wonder, question. Life that could look up at the night sky and ask, how big is the universe? And now we have an answer, or at least the beginning of an answer. The observable universe is 93 billion light-years across. It contains trillions of galaxies, septillions of stars, more planets than we can count, and somewhere, in all of that vastness, here we are, thinking about it, talking about it, trying to understand. It's quite extraordinary, really. Take a moment and think about your place in all of this. You are on Earth, a planet about 8,000 miles in diameter. Earth orbits the Sun at a distance of 93 million miles. The Sun is one star in the Milky Way, about 26,000 light-years from the center. The Milky Way is one galaxy in the local group, which is part of the Virgo supercluster, which is part of Laniakea, which is part of the cosmic web, all within the observable universe. 93 billion light-years across, and beyond that, perhaps, infinite universe. You are a tiny part of something unimaginably vast, and yet you're here, conscious, aware, thinking about it all. That's special. That's meaningful. The universe gave rise to stars, and planets, and life, and consciousness. And now, the universe can contemplate itself. Through us, we are the universe, becoming aware of itself. That's a profound thought. So, how big is the universe? It's big. 93 billion light-years across, and as far as we can observe. But more importantly, it's amazing. It's beautiful. It's full of wonder. And we're lucky to be able to experience it, to learn about it, to think about it, to be a small part of this vast cosmic dance. Thank you for joining me on this journey. I hope you found it relaxing, peaceful, maybe even inspiring. Remember, whenever you look up at the night sky, you're looking out into the universe. Those tiny points of light are distant suns, each one, possibly, with worlds of their own. And beyond what we can see, there's more, perhaps infinitely more. But for now, rest easy. The universe is vast, but you're here, safe, comfortable. You're part of it all, connected to it all. Take a deep breath, relax, and if you'd like, close your eyes. Let your mind wander through the cosmos we've explored today, from Earth to the Moon, to the Sun, to distant stars, to galaxies far away. All of it part of the same universe, the same reality, and all of it, in its own way, connected to you. You're made of atoms, from ancient stars. You're part of the universe, experiencing itself. That's something special, something worth appreciating. So rest now, sleep if you'd like. Dream of distant galaxies, of stars being born, of planets orbiting far away. Dream of the vastness and the beauty of the cosmos. And know that, in all of that immensity, you have a place right here, right now. You are where you're meant to be. Thank you for listening. Good night and sweet dreams.